Hey everybody, hope you guys are doing well, staying out of trouble and getting outside, getting some fresh air on these beautiful days, going for a walk, bike, whatever. Just get outside, get some sun, build up that vitamin D, work on that great tan by being outside and being active. Okay, today we are doing electrolytic cells. So we've spent a bunch of time on voltaic cells. Yesterday was the fascinating lesson on corrosion, rusting, and today we'll get all the theory. So this is kind of like when we started chapter 14 and day one was theory on voltaic cells and how they work. So today is theory on electrolytic cells and how they work. And then tomorrow is a whole bunch of practical examples, interesting ways we use electrolytic cells to make all kinds of awesome things. And then on the next day, we're doing electrochemical cell stoichiometry or cell stoic. So that'll be Thursday, and then we're done chapter 14 and wrapping it up on Friday. Insanity. That means we're 3/4 of the way through the course. And we have one unit left to do. Awesome. Awesome. We are going to finish early. Guaranteed. Okay, so let's dig into this. In your study guide, the notes are page 228. And I'm going to be ripping through this pretty quick today. Lots of this stuff is knowledge that you kind of already have. We're just applying it to electrolytic cells. So let's take a look at this example. We have looking at the cell notation, we have a lead zinc sulfate lead cell. So lead electrodes, both anode and cathode, and then the zinc sulfate would dissociate into zinc 2+ and SO4 2-. So what have we got for players? We have lead and we have zinc 2+. So you will notice by looking at this that the oxidizing agent is well below the reducing agent. So it is non-spontaneous. Okay. Cell potential for this, if we were going to calculate it, we have all our cell potentials here. So cathode, strongest oxidizing agent. Anode on this side, strongest reducing agents. So cathode minus anode, cathode minus anode for our cell potential is negative 0.76 volts minus negative 0.13 volts, which works out to be, so that becomes a positive, and that becomes negative 0.63 volts. Negative meaning non-spontaneous. Negative cell potential equals non-spontaneous. Okay. Second electrolytic cell, and I'm using the word electrolytic because that's what non-spontaneous cells are. They're electrolytic. So second example, copper solid, iron 2 sulfate, copper solid. So we know that copper will likely be our strongest reducing agent, and we have Fe2+ and SO4 2-. So if we went searching on our table of relative strengths, we would find Fe2+ there and copper 2+ there. And they're also built in right here. So Fe2+ and copper solid. Yeah, I don't know why I said copper 2+, because there wasn't any. It is copper solid and Fe2+ down here. That's the one we're looking for because we don't have any copper 2+. Okay, so cell potential for that one. Cathode is our strongest oxidizing agent, Fe2+, negative 0.45 volts, minus anode, which is the copper solid at positive 0.34 volts. Negative 0.45 plus 0.34 is negative 0.1. Oops, let's try that again. Negative 0.45 minus positive 0.34 is negative 0.79. Again, negative. So what does a negative cell potential mean? Non-spontaneous. So hopefully I've beaten this point to death. Electrolytic cells are non-spontaneous. The oxidizing agent is always below the reducing agent. So summary for your notes. Electrolytic cells are non-spontaneous. We just went through that. Because they're non-spontaneous, they have to be hooked up to a power supply to make them work. The electrons don't spontaneously flow from the strong oxidizing agent down to the strong reducing agent. They have to literally be pushed uphill, is one way to think of it. You use that damn good analogy I gave you with water always flowing downhill. If you want the water to flow uphill, you need to push it. If you want the electrons to flow uphill, you need to push them. So they're non-spontaneous and they need a power supply. Those are in red because they are different than a voltaic cell. They still contain two electrodes. They still contain an electrolyte, so that part is the same as a voltaic cell. Codger still applies. The cathode is still the strongest oxidizing agent. The anode is still the strongest reducing agent. Nothing's changed there. Cations still flow to the cathode. Anions to the anodes. All of those things haven't changed. Here's a new one. They have no salt bridge. The reason they don't have a salt bridge is you don't need it because you're already pushing electrons anyway, so you're not worried about the charge building up and it becoming harder for electrons to flow. It's already hard for electrons to flow. We have to push them. And the last one, the cathode is labeled as a negative sign. So on voltaic cells, this would be a positive, but on electrolytic, it's a negative. And the anode is a positive. So we've reversed the signs, and that's just a convention or a rule. The reason is to remind you that when electrons are flowing towards the cathode, because remember I said the cathode still gains the electrons, they don't flow spontaneously, they have to be pushed. If we had this as a plus sign, you'd be going, well, that doesn't make sense. Electrons are attracted to the positive. Okay, well, then it's not positive. It's negative and it repels electrons. You have to push them with the power supply. So this is the basic design of an electrolytic cell. Pulled electrons pulled from the anode, pushed to the cathode using a battery or a power supply. And ironically, a battery is a voltaic cell. So you could use a voltaic cell to run this electrolytic cell. Some people are thinking, why would you do that? Okay, well, we'll get there. Here's the little rule about the negative cathode and the positive anode. So in a voltaic cell, the cathode is labeled positive and the anode is labeled negative. But in an electrolytic cell, it's the reverse. Okay, moving on. I said we're going to go fast. Fasten your seatbelt. Okay, we're going to fill in this chart. So in a lot of ways, electrolytic cells and voltaic cells are opposites. And sometimes you'll see voltaic cells called electrochemical. That's kind of a catch-all for both voltaic and electrolytic. So I like using the terms electrolytic and voltaic. All right, energy conversion. So in a voltaic cell, we have stored chemical energy. The oxidizing agent gains electrons from the reducing agent, and that chemical energy is converted into electricity. An electrical current flows. Electrolytic cells are the opposite. In an electrolytic cell, it's electricity that's being used or a power supply to make chemicals. So complete opposite. Okay, spontaneous. Which ones are spontaneous? Voltaic cells are. Electrolytic are not spontaneous. Let's just go yes and no. The value of the electric cell potential, positive because it's spontaneous, negative, non-spontaneous. Okay, in an electrochemical cell, a spontaneous redox reaction creates an electric current, or in a voltaic cell. In an electrolytic cell, the reverse occurs. Electric current is required because it's a non-spontaneous reaction. Why use them? Well, the reason you would use an electrolytic cell is to make products, okay, to make stuff. So they use up energy, but they make a lot of useful products that are worth a lot of money, as you'll see tomorrow when we look at a whole bunch of electrolytic cells and what they do. Okay, let's motor on. This little diagram's just saying that a voltaic cell produces electricity as a product going that way, and an electrolytic cell uses up electricity going the other way. Okay, this chart is in your notes. If you would like to pause the video here and fill it in, you could do that. Everything is provided there. I think it's pretty straightforward. It's just a second summary of all the things that I just said to you guys, comparing voltaic and electrolytic cells. Okay, I'm going to move on to go through 4 examples of these things with you. What do they look like? How do you draw them? What's all of the things that you need to know for electrolytic cells? And then we're done. So what is it going to be, like 4 minutes each? 4 times 4, 16 times the square root of 1. Okay, and then divide that by 1. You get 16. Good. Okay, you're with me? Some tricky math there. Okay, a potassium iodide electrolytic cell. So determine the half reactions occurring at the cathode and the anode for an aqueous potassium iodide. So here's what it looks like in solution. This is kind of like 5-step method. We have K plus, I minus, and water. That's it. Those are the only things present. What do we know about carbon electrodes? They are inert. They won't take place in the reaction. They're just there to conduct electricity. Here's our power supply, which also tells us this is electrolytic. Okay, it's an electrolytic, non-spontaneous. Needs a power supply to work. Okay, now looking at this thing, the electrodes are flowing this way. So that means this is our cathode. Electrons are still gained by the cathode, so we're going to label it as a negative on this electrolytic cell. Anode, label it as positive, opposite to a voltaic. Okay. Now, what did we need to do again? To determine the half reactions occurring at the cathode. Okay, so cathode is our strongest oxidizing agent. So what is it? We have 3 things to choose from: K plus, I minus, or water. So let's go searching. Strongest oxidizing agent is, there's K plus, and there's water. Okay, who's stronger? Water is. Interesting. Okay, so our strongest oxidizing agent is water, and its half reaction is 2 waters plus 2 electrons makes hydrogen gas and 2 hydroxides. Believe it or not, that says aqueous. Okay. Strongest reducing agent. We can go searching again. K plus, I minus, water. So K plus, I minus, water. And here is water. And here's I minus. Okay, remember they get stronger as you go down. So it looks like on this one, 2I minus is the strongest reducing agent. Anode. 2I minus. Lose 2 electrons and become iodine. Solid. Okay, determine the half reactions of the anode. Okay, and cell potential. So we don't need to add this one up. If we did, the electrons are already balanced. We would just cancel out, bring things down, and electric cell potential, cathode minus anode. So on this one, I minus, our anode is hidden by my face, positive 0.54, and water is negative 0.83. Okay, so cathode, negative 0.83, minus anode, positive 0.34, positive, where is it again? Positive 0.54. So that is negative 0.29 volts. Non-spontaneous takes 0.29 volts of power to get this thing to run. 0.29 volts is what we'd have to set the power supply at, actually greater than. So 0.3, 0.31. If you want to speed it up, add a little more. Okay, diagnostic tests. What could we use for diagnostic tests? Okay, hydrogen gas, pop test. We're producing hydrogen gas. That's number one. Hydroxide. That's going to be basic. So pH increasing due to OH minus. And we're also making iodine. There's lots going on here. So this would be a red, brown, solid, I2. 3 different things we could look at. Wow. Okay, moving on. Voltaic cell number 2. So this is an electrolytic cell containing carbon electrodes and a sodium sulfate solution. Carbon electrodes and a sodium sulfate solution. So Na plus, SO4 2 minus, and water. 5-step method. These are the major entities present. So now we go searching. Na plus, SO4 2 minus, and water. Let's get a better color going here. Na plus, SO4 2 minus, and water. Okay, so we know we have water here. Na plus, SO4 2 minus, and water. Na plus is way down here, really weak oxidizing agent. Here's water. Water is a stronger oxidizing agent than sodium. SO4 2 minus, I saw it in here, but it only works with other things like lead, and there's no lead. So strongest oxidizing agent is water. Strongest reducing agent is water. Wow. This is a water-water electrolytic cell. That's crazy. Okay. Predict the reactions at the cathode and the anode. Cathode is our strongest oxidizing agent, water. 2 waters gain 2 electrons to give us hydrogen gas and hydroxide ions. We just saw that one. 2 hydroxide ions. Just verify that. Yes. 2 hydroxide ions. Let's clean that up a bit. Okay, there's our cathode. Anode is also water, and the anode is 2 waters. Lose 4 electrons and O2 gas and 4H plus. Interesting. Interesting. Okay. Now, predict the reactions and the overall. Okay, so we need the overall reaction. I like this one. It's interesting. Okay, so we're going to switch colors here. 4 electrons lost, 2 gained. So we need to double everything. 4, 4, 2, 4. Okay, now we can add it up. So we have 6 waters. Electrons are gone. 6 waters makes 2 H2 gas plus 1 O2 gas plus 4 OH minus and 4 H plus. These combine to make 4 HOH or 4 waters. So I have 6 waters here and 4 here. That could also be written as 4H2O, same thing. Now we can simplify this. Take 4 away from both, and we're left with 2. So this is the net reaction. 2 waters makes 2 hydrogen and 1 oxygen. Okay, draw and label a cell diagram. So I'll do that in a sec, including power supply. What minimum voltage must be applied to make this cell work? Okay, so here's how you draw and label an electrolytic cell. Super easy. Here's our electrolyte, which is Na2SO4, aqueous. 2 electrodes, carbon, color them in. Power supply can be labeled with a plus/minus. So we got a power supply hooked up to our electrodes sitting in our electrolyte. We need to label one of them the cathode, which is a negative. The other is the anode, which is positive. They're both carbon solid. And I'm going to put electrons going towards the cathode. And I think that's about it. Calculate the cell potential. And did I do this one in advance? I did not, so let's take a look at it. Water, so our cathode is negative 0.83. Minus our anode, water way up here, is positive 1.23. Negative that minus that is 2.06 negative volts. So this thing needs at least, or we'll say greater than 2.06 volts to work. So if you want to split water into hydrogen and oxygen, you have to add at least 2.06 volts, or preferably more, 3, 4, 5 volts, in order to push those electrons towards the carbon cathode and split the water in the process. Diagnostic test. Okay, we got lots. We have oxygen gas, so we could do glowing splint relights or pop test for hydrogen gas. If you wanted to go right into the 2 cathodes, at this cathode you're making hydroxide. You could do a litmus test. It would be turning blue at that half cell, and it would be turning red at that half cell. So if you can catch them before they combine to make water, you could test pH as well. So there's lots going on with that one. So if I had given you the answer, here's what it would have looked like, nice and neat, with all that same information drawn out for you, and you're using test tubes with your cathode and anode. So you'd have your 2 metal electrodes sitting inside there and the gas bubbles coming off as you're forming those products. So that's a neater version of what I just drew. Now there are 2 more of these that you can do in your notes. So I am going to get you to pause the video. I'm going to do the same, and I'm going to answer these ones. I'm not just going to answer them while you're watching me. I will answer them and then come back to the video and go through them to save a little bit of time. So try them on your own, see how you do by then coming back and doing part 2 of the video to see how things work for you. Okay. Hopefully it goes well, and I'll see you in a little bit of time here.